Hello, my name is Arno Smets. I'm professor in the Photovoltaics Materials and Devices group at the Delft University of Technology. Welcome to the first course in our solar energy program. This course is called Solar Energy, the Fundamentals of Photovoltaic Energy Conversion and the Role in the Energy Transition. In this course, you will be introduced to the physical principles of the photovoltaic energy conversion that takes place in solar cells, and you will learn about the role of solar energy in climate change mitigation and rural electrification. I've already introduced myself, Professor Arno Smets, and I will be accompanied by Dr. Thierry de Vrijer, who is a researcher in the Photovoltaic Materials and Devices group. Our group has expertise in online and on-campus teaching and research in all aspects of photovoltaics, from fundamentals to device fabrication and full system design. This course is split into 4 parts. The first week serves as an introduction to the role of solar energy in the energy transition. In the rest of the course, we focus on the physical principles of photovoltaic energy conversion. In week 2, we look at the working principles of a semiconductor-based solar cell. Week 3 is all about the optics for solar cells, which is an introduction to light management for maximizing light absorption. In the final week of this course, we will look at all the concepts introduced in the course and find out how they result in electrical losses in solar cells. This last week, we will give you the tools needed as photovoltaic expert to properly design and engineer solar cells. Let's go through all of these 4 sections in a bit more detail. The course starts with a broader perspective on the role of solar energy. We will start by looking at climate change, the principles behind it, and the different global warming scenarios from the most recent reports of the Intergovernmental Panel on Climate Change, the IPCC. We will then look at the transition from a society reliant on a fossil-based energy system to a sustainable energy system. Besides the energy transition, we also discuss the role of solar energy in the access to electrical energy. After these videos on the energy challenges, we will discuss the concepts of energy and power, followed by the major technologies available for renewable energy conversion. For each technology, we will consider the physical principles of energy conversion and their potential advantages and limitations. We will then continue with the principles of photovoltaic energy conversion. We will look at solar radiation, the history of photovoltaics, and recent developments. Finally, in the first week, we will consider a number of important metrics for photovoltaics. These metrics will help you assess the potential for different solar cell designs, PV module architectures, and PV technologies for different applications and locations. We will then look at the very basic concepts of a solar cell. Why can a solar cell convert light into electricity? What are the basic processes that are responsible for this effect? How is a solar cell built up? We will answer questions regarding the atomic structure of a semiconductor material and the existence of mobile charge carriers, electrons and holes, and how their concentration can be manipulated by doping. It is important to know the concentration of electrons and holes in a solar cell because they are the carriers of electricity. You will learn how these charge carriers move around in a solar cell and how extra charge carriers are generated or annihilated in a semiconductor. It is necessary to know these processes in the solar cell in order to properly understand how a solar cell produces electricity. We will then move from semiconductor physics to optics. Here we will discuss the light management in a solar cell. The most basic idea of light management is how to capture the most light with the least amount of material in a solar cell. We will start with the behavior of light as a wave and particle and discuss the interaction of light inside a medium and at the interface between two different media. We will then look at the fundamental spectral losses in solar cells, as well as other optical losses. Having covered optics and semiconductor physics, in the final week of the course we will focus on the design rules of solar cells. Here we will translate all the physical principles discussed in the course into different loss mechanisms that occur in a solar cell. Finally, we will distill from these loss mechanisms a set of design rules for the optimal solar cell design. All the video content in this course, as well as numerous ungraded practice assignments, are available for free. These exercises are meant to test and improve your understanding of the concept discussed in the videos. So try the exercises and don't be afraid to make any mistakes. By upgrading to the verified learner experience, you will get access to all exercises, the practice and graded assignments, and exam questions. Note that details about the assessment and grading scheme for this course can be found in the course syllabus. We strongly recommend following along in this course with our textbook Solar Energy, Physics and Engineering of Photovoltaic Conversion Technologies and System. This textbook is available as a free ebook for any e-reader on Amazon. Hard copies are also available for purchase at Amazon.com as well as other retailers. On behalf of the entire photovoltaic materials and devices team here at the Delft University of Technology, I'm very excited to provide this course for you. I hope you are ready to go jump right in and become an expert on the fundamentals of photovoltaic energy conversion and the role in the energy transition. See you in the next video lecture.